So this video follows directly on the heels of at the end of the previous video, which was what happens when we have a mixture of both a weak acid and its conjugate base. How can we think about what the pH of that system is? So we're going to jump right into an example because you have all the mechanics to solve this, but we need to see it in operation. So the example is, what if we take zero point 0.1 moles of acetic acid, which we already know to be a weak acid, and its conjugate base, sodium acetate, and the sodium here, remember, you can't just have acetate ion, you can't have negatively charged species in a bottle on the shelf. They have to be neutral, and so the acetate ion is being carried by the sodium. The sodium is just the spectator here. And we toss those both in a full liter of water. So what's going to happen to the system? How is it going to move? How's the equilibrium going to be established here? And then what would the final pH be? Those are our targets. So of course we need an ice table. We need to understand what our initial change in our equilibrium condition is. The equilibrium is what we're after here, but this looks slightly different than what we've seen before. So what we've seen before is we just add one of the reactants to the system and then we allow that to shift, and it's pretty obvious the direction it's going to shift and how to solve that problem. What we have now is we have two different things in the system to start with, and we need to figure out what the direction is so we can understand where do we add and subtract x's in the change here, and then how do we figure out what the final concentration of hydronium is, which is pretty straightforward. So the first question is, which direction is this going to move? And that one actually is pretty easy, or easier than you think, especially in a situation like this where we have zero of one of these things. We know that an equilibrium constant K is going to be the products divided by the reactants. In this case, this value can't be zero for K to be a real number, otherwise the whole thing becomes zero, right? And so in that case, we can sort of deductively reason that this system, when mixed together like this, it must shift in this direction because that zero can't be zero. It's got to increase from a non-zero value, so it has to move to the right. And the extent it moves to the right is what we're going to figure out, but that's the first step because it now allows us to say, well, this must be a minus x, that's negligible, then this is a plus x, and this is a plus x, as opposed to going the other direction if the equilibrium were to be the other way. So at this point, it's probably nice to consider what is the common ion effect, and really what that means is it's this idea that we already have a common ion to whatever is going to be produced, in this case from the dissociation of the acid. What I mean by that is if I were to just take acetic acid and let it dissolve, it's going to produce the acetate ion. But we already have a common ion in solution. We have the acetate ion, but it came from sodium acetate that we added separately. That's the origin of the name common ion effect. It already exists. It's common to the acid that's dissociated. We can also logically probably figure out not the number, but just sort of looking at this and reasoning through it. If we had zero of the acetate, if we didn't have the common ion effect, we would expect probably that the equilibrium is going to move further to the right to produce more of both of these things, such that it satisfies K, the equilibrium constant. But if we already have some of this in solution, then the system doesn't need to shift as far to the right to actually get it to satisfy K. And so we can sort of intuit here the extent of the dissociation is going to be less when we already have some of the acetate there than when the acetate was absent to begin with. So those are the sort of intuitive things that we want to be sort of thinking about because it can help us rationalize what's happening here. So I'm going to go ahead and write up just the equilibrium expression for this, Ka. We can just look it up. It's 1.8 times 10 to the minus 5. I forgot to include this as an important part here in our, oops, I wrote this a little wrong. There we go. This value at equilibrium should be x plus whatever was originally there, so that's plus 0.1. So I've neglected to write that because I forgot about it, but it's important because that means when we substitute it into the equilibrium expression, which is acetate times hydronium, that's going to be x times x plus 0.1 on the numerator divided by 0.1 minus x in the denominator. So let's make an approximation that x is small and see if we can make an initial pass at a solution. And if we assume x is really small, then what we're really saying is this x in the numerator is negligible or 0. This one is also negligible or 0. And so this becomes x times 0.1 over 0.1 goes away. And so Ka is nominally equal to x, which we already know Ka here. Quick test to that approximation is take x divided by what the original concentration of that acid was times 100%. We get 0.02%, far less than our 5% criterion. So we say that's a fair approximation in this case we'll use. So that allows us to take negative log of x, because x is the hydronium ion concentration. We get a pH of 4.74. Why all this work? It seems pretty much the same as before. Well, remember, what we have different about the system is this common ion. We had 0.1 to begin with, and we sort of intuited that the extent of dissociation for acetic acid when there's already some of its conjugate base present is going to be less than if there were no acetate already present. So let's compare what the pH would be if there were no acetate to begin with. See if you can make a prediction. Are you expecting the pH to be higher or lower than when we already have this common ion present? Okay, so I wrote this up pretty quickly. I just wrote a second ice table down here because it's the same reaction, but we're starting with 0 of that common ion acetate. Everything else is identical. And we predicted probably that there's going to be more dissociation in this case because there's less of the product that's already there. And so if we solve this out, you get x is equal to 1.3 times 10 to the minus 3, which is considerably larger than the 1.8 times 10 to the minus 5. It's about a factor of 100, which translates to 2 orders of magnitude in the pH. So 4.74, if we already had some of the acetate, the common ion there, 2.87. Remember, this is a logarithmic scale, so that's a 100-fold increase in the concentration of protons when we don't have the common ion there. So that's really the gist of what the common ion effect does in equilibrium, which really falls out of Le Chatelier's principle. So I think it's a pretty intuitive result. All of this work with the common ion effect and thinking about neutralization reactions gets us to the next topic, which is buffers. And buffers are really these systems where we have both the weak acid and its conjugate base in system at the same time, and the unique benefits that provides.